Which leads us to, drum roll, the most beautiful equation in the universe. In all of creation, the most beautiful equation. If you're abducted by aliens and they say, we'll let you go, if you tell us the most beautiful equation in the universe, I've got the answer for you. It's your ticket to freedom. The most beautiful equation is e to the I pi power plus 1 equals 0. Some people write this as e to the I pi power equals -1, but I think it's more beautiful to write it like this. Why is the most beautiful equation in the universe? By the way, I is the imaginary unit. If you didn't know, one of two numbers whose square is -1. Don't worry about whether it exists or not. I'll address that in a few minutes here. Why is this the most beautiful equation in the universe? First of all, it's got the three most important operations in the universe: addition plus, multiplication, I times pi, and exponentiation, raising to a power. Three most important operations. It's got the five most important numbers in the universe: 0, 1, pi, e, and I are the five most important numbers in the universe. Now, a physicist might argue, what about c, speed of light, or h bar? What is that? Planck's constant divided by 2 pi or something. It's related to quantum mechanics. Aren't those numbers just as important as these five? My argument is they are not numbers. Did you know that physical constants are not numbers? No, they're not. They are physical constants, not numbers. Why are they not numbers? Don't we use calculators with them? Their numerical values depend on the units you use. That's why they're not numbers. We've got our standard units, of course, but we could use non-standard units and we'd get different numerical values based on those new units. That's why they're not numbers. So yes, these are the five most important true numbers. And also equal sign, well, that's the most important equivalence relation is what it's called in the universe. In one simple equation, and it's true. Why is it true? Let's write it as 1 plus e to the I pi and see if we can figure out why it's true. Now, what I'm about to do is not really a proof. I'm not doing any proofs today. It's all hand-wavy math, like magic, poof, poof, poof. Not really rigorous arguments. I'm not done yet. Not really rigorous arguments. They are intuitive arguments that seem reasonable and do seem to verify things, but they're not really rigorous. Then the first non-rigorous thing I'm going to do here is I'm going to use the series for e to the x and replace x with I pi. Series for e to the x starts out 1 plus x, I pi, plus x squared over 2 factorial, right? Remember that from 20 minutes ago? 15 minutes ago? X squared over 2 factorial. I pi squared over 2 factorial. Plus x cubed over 3 factorial. X to the 4th over 4 factorial. X to the 5th over 5 factorial. Etc. You're just trusting me that I can do this. Why can you do this? What does I even exist, for one thing? The imaginary unit? Imaginary numbers? Are you kidding me? There's no philosophical question about whether imaginary numbers exist. Nobody does philosophy about that. They definitely exist. Why? Because we say so. That's why. We define them to exist. The only questions are, if we define them to exist, do they make a coherent number system? Yes, they do. Are they useful? Yes, they are. Very, very useful, actually. And are they interesting? Yes, they are. Very, very interesting, in fact. In fact, complex analysis, which is about complex numbers, which involve the imaginary unit I think is the most interesting, beautiful area of math. In all of math, I personally think it's the most beautiful. I'm not an expert in it, but I think it's the most beautiful. It's got astonishing results. If you ever get a chance to take complex analysis, even as an engineer in grad school, do it. It's astonishing. It's amazing. And it is useful. Okay? Definitely useful. I'll try to hint at some applications at various times in the rest of the semester. Here, how does it help us? Rearrange this infinite sum as follows. First, group all the terms that do not involve an I together, meaning really the even powers that you see there, because in this one, we'll use the fact that I squared is -1 to get rid of the I in that even power. In this one, we'll use the fact that I cubed is, well, I guess that's got to be -1 times I. Yeah, -I. In this one, we'll use the fact that I to the 4th is I squared squared. -1 squared. +1. I to the 5th ends up being 1 times I itself. I to the 6th ends up being I squared, -1. I to the 7th ends up being -I. I to the 8th power ends up being +1 again. It's cycling. It is. All the even powers, the I goes away. With appropriate signs, negative with the 2nd power of pi, positive with the 4th power, because I have an I to the 4th, which is +1. Back to negative again, it turns out, with the 6th power, etc. And then group together all the odd powers of I, factoring out an I as well. What am I left with? I got a pi there. Over here with that term, I've got a minus pi cubed over 3 factorial. Why a minus sign? Because of the negative I there. I cubed is -I. Then with the 5th degree, I'd have I to the 5th, which is I. That's a positive pi to the 5th over 5 factorial. And lo and behold, that amazingly is the series for cosine with pi plugged in. And this amazingly is the series for sine with pi plugged in. We know cosine of pi is 1 and sine of -1, excuse me, and sine of pi is 0. So this simplifies to 1 minus 1 plus 0I is 0. Done. 1 plus e to the I pi equals 0. What's the hand wavy stuff? The hand wavy stuff is saying we can do everything here. You know, how do you really know you can do all that? It's partially by definition. It's partially justified by rigor with understanding convergence of series. Is it a useful equation? It does turn out to be useful. Okay. Imaginary numbers are used all the time in electronics of all things, and also in quantum mechanics. All the time they're used. They're also used in math classes like differential equations.